to everyone. You're welcome to this video where we are going to solve a special problem that has to do with Bernoulli equation. So in this video, we are going to see how the parameters in the differential equation actually affect the solution. So we're going to consider just only one example, and the problem is also in your lecture material. So let's consider this problem. The y dx is equals to ky minus my squared. But the only thing about this problem is that k must be greater than 0 and m must be greater than 0. What does that mean? It means that k and m, they are real value constants. They are positive constants. They are positive integers. So the first thing we need to do is this. Let's try to rearrange the problem. So when we rearrange the problem, you now see that the problem we're having now is in terms of it looks more or less like linear, but there is a problem on the left hand side, on the right hand side, where we have minus my squared. And now in this case, we are having the dependent variable raised to power n, and here n is 2. Then that means that the problem we are dealing with is a typical Bernoulli equation. So how do we solve Bernoulli equation? Don't forget, the problem is this: we look for the real dependent variable raised to power integer n, and we divide both sides by that same thing. So in this case, we need to divide both sides by y squared, because it is only y squared that is making the problem Bernoulli. Because I think we don't have y squared there, then what we have is what is a simple linear equation. So in this case now, when we now see clearly that the problem at hand is indeed Bernoulli, so we need to divide both sides by y squared. That will help us to obtain equation 2. Don't forget that you have 1 over y squared multiplied by the y dx, and that simply means y raised to power minus 2. And for the other one too, you have minus ky divided by y squared. And don't forget that by the time y squared come up as a numerator, we're going to have it to be y raised to power minus 2. Then in that case, you can have y multiplied by y raised to power minus 2, and that one will definitely give me y raised to power minus 1. Then the other side we have minus my. So what is the next thing now? Don't forget, we now look for the coefficients of our key of x. And in this case, what is it? Something that is y raised to power minus 1. So we now select z to be equal to y minus 1. Don't forget, z is not like another dependent variable. So that means that with that, we can now go straight and reduce the problem to linear differential. Now that we've assumed y raised to power minus 1 to be z, what is the zy? Don't forget, in this case, very simple. So minus 1 will just come down to multiply it. Then we have minus 1 minus 1. So in that case, we have our dz dy to be minus 1 raised to power y minus 2. So what is the next thing? The next thing is for us to use what is called chain rule. And here, we are looking for the rate of change in z with respect to x. Meanwhile, we only know that z changes with y, and we know that y changes with x. So what do we need? We need to use chain rule, which means that the z dx is equal to the z dy multiplied by the y dx. So in that case, we need to substitute the z dy. And by the time we substitute the z dy, then we have this expression. Then don't forget that we need to multiply both sides by minus 1. Then we obtain our equation 3. Now that we obtain our equation 3, we need to now go extra miles to substitute equation 3, and at the same time z equals to y raised to power minus 1 into our equation 2 that we can see now. So if we do that, we return that back. Then we now have minus the z dx minus kx is equals to minus m. So which means that we can also multiply both sides by minus 1. So that one will now give us a simple linear equation, which is our equation 4 that we are very familiar with. Then the next thing we should be thinking now is that how do we solve equation 4? Then we now come up with what is called integrating. The major problem we always have is is how to come up with our integrating factor. That is, if we are solving linear equation. And equation 4 here is the same problem. So what do? We look for p of x, and in this case, what is our p of x? Our p of x is what is k. So which means that we need to obtain our integrating factor. So how do we get our integrating factor? Is the same thing as exponential integral p dx. And by the time we return our p of x, which is k, then we need to integrate k dx. And don't forget that imply means that we are trying to integrate k, then x is power 0 the x. So that one will give us exponential kx, because by the time you integrate k multiplied by s to the power 0 dx, what we have is what is x. So we have exponential kx to be our integrating factor. So the next thing now is that we multiply both sides of equation 4 by the integrating factor. So in this case, we have exponential kx to be multiplying dz dx plus kz as well is also multiplying by exponential kx, and at the same time our m is multiplying exponential kx. That is how we obtain our equation 5. Now the major question now is this: is there any way we can rewrite our left hand side of equation 5? Yes. And the only thing is this: if you have ddx into bracket the dependent variable we are looking for, then multiply by exponential kx, which is the integrating factor, then you see now that this expression, which is our left hand side, is the same thing as the left hand side of equation 5. Let's see, for instance, now if you keep your z and you differentiate exponential kx, what we have will now be k exponential kx, which is the second term, left hand side of equation 5. If we should keep your exponential kx and you differentiate z, what we have is exponential kx dz dx, which is the first term of left hand side of equation 5. You can now see now that we are very correct. We can rewrite equation 5 to be ddx into bracket the dependent variable we are looking for multiplied by the exponential kx. So let's integrate both sides. By the time we integrate both sides, you see that the integral will take care of derivative. So down we go, then we now have our z multiplying by exponential kx. Then what about if we want to integrate exponential kx dx? How do we do that about that? We differentiate the power of exponential, and if you differentiate kx with respect to x, we have k. Then you divide it by it. That is why you see m divided by k. If it's differentiation, we multiply, but if it's integration, we divide. So that's why we now have m divided by k exponential kx plus c. So let's now divide both sides by exponential kx, because it's only exponential kx that is multiplying our z. So if we divide both sides, we now have our z equals to m divided by k, then plus c exponential minus kx. Don't forget that c divided by exponential kx is the same thing as c multiplied by exponential minus kx. So that exponential kx will come up, then the power will change to negative. So the next thing is for us to now return our z, which is y inverse. So by the time we return our z, which is y inverse, then we have this expression. We can find the LCM of the right hand side. That will give us m plus ck exponential minus ks over k. Then we can return everything and make y now the subject of the formula. So we can have our expression to be y is equals to k divided by m plus ck exponential minus ks. Now if you look at this solution now, there are many things involved which will not be the major concern that I was saying the other time. Don't forget that from the problem we have m to be a parameter greater than 0, we have our k to be a parameter greater than 0, and now we've obtained the solution. Then what are the things we can notice? Because here we are now dealing with a parametric equation. We have parameters in the differential equation, and this parameter, they play a lot of things. They help us to determine the nature of solution, because the parameter they can take any values, and the values will definitely affect the solution, which is also dependent on the parameter. Now if you look at the solution again, now before we even look at this, let's take a look at the problem again. The y dx is equal to ky minus my squared. Now let us try to factorize y from the solution. We now see that we are having y into bracket k minus my. You see that? So that is what we are having there. But from this now, we cannot see clearly now that there are two things involved. It's when y is greater than 0 and when y is less than 0. But when y is less than 0, there's no problem with that. Because, why did I say there's no problem? Hey, thank you. I'm saying there's no problem with the case of y less than 0, because if you look at the function fx comma y, when y is less than 0, that means that y is a negative. And by the time you multiply that negative by the bracket, you will see that that negative will multiply minus my. And that will now give us positive. So that is why when y is less than 0, we have a negative. But if you look at inside the function, we already have minus my. And minus and minus will give us what? Will give us positive. So there's no problem with that case now. But let's take a look at the case when y is greater than 0. There are two things involved when y is greater than 0. Number one is when k minus my is greater than 0, and when k minus my is less than 0. These are the two factors. So in this case now, you now see that this same problem we are talking about, which is Bernoulli, it gives us 3 different cases of solution. So if you open your lecture notes now to page 39, you will see how your tutors the program developer have explained these 3 cases to you, because we are dealing with parameters. K and M are parameters. Although actually we've been posing the question that M and K, they must be greater than 0. That is fine, but to make it more practical, we need to bear in mind that what if K is a positive greater than 0? What if M is a positive greater than 0, and at the end of the day K minus My is greater than 0? Then that is when we are now bringing this to you, that there are 3 different cases to this solution, which you can see in your lecture notes. Thank you very much.